All right. Hey guys, I am back after some dinner. Uh, let's see. Understanding ownership. So I'm just going to bang out chapter 4, see how long that takes. If this is quick, it doesn't look like it's going to be quick. Oop, yeah. Yeah, it'll take a minute. So let's just do chapter 4. We'll see how far we get. There are some things that I realized that I forgot to look over. Prelude contents. I think maybe I'll go over this. I kind of looked at it myself to see what was in the prelude. This, if you remember, is the standard library that's automatically imported for you. Here's the additions guide, which I'm not going to go over. Appendix A, I think I said I was going to go over this. I wasn't sure if word was a keyword. There's not that many keywords, so that's good. Yeah, I think tries reserved for future use. That's funny. Constant evaluation. Oh, okay. And this is, things that you can put in a constant expression versus what you can put in a let, I think. Okay. Then we don't need this anymore. All right, awesome. So let's just bang out chapter 4. Understanding ownership. Ownership is Rust's most unique feature and has a deep implication for the rest of the language. It enables Rust to make memory-safe guarantees without needing a garbage collector, so it's important to understand how ownership works. In this chapter, we'll talk about ownership as well as several related features, borrowing slices, and how Rust lays data out in memory. Okay. Let's see. What is ownership? Ownership is a set of rules that governs how Rust program manages memory. That's interesting. I didn't think it had anything to do with memory management. Yeah. Okay. Well then, let's keep reading about this, because obviously I don't understand ownership whatsoever. All programs have to manage the way they use computers' memory while running. Yeah. Some languages have garbage collection that constantly looks for no longer used memory as the program runs. In other languages, the programmer must explicitly allocate and free the memory. And I believe that's like in C, you can use malloc and stuff, which I never was good at. Rust uses a third approach. Memory is managed through a system of ownership with a set of rules that the compiler checks. Okay. If any of the rules are violated, the program won't compile. None of the features of ownership will slow down your program while it's running. Because ownership is a new concept for many programmers, it does take some time to get used to. The good news is that the more experienced you become with Rust and the rules of the ownership system, the easier you'll find it to naturally develop code that is safe and efficient. Keep at it. When you understand ownership, you'll have a solid foundation for understanding the features that make Rust unique. In this chapter, you'll learn ownership by working through some examples that focus on a very common data structure, strings. All right, let's read this. The stack and the heap. Many programming languages don't require you to think about stack and heap very often, but in systems programming languages like Rust, whether a value is on the stack or the heap affects how the language behaves and why you have to make certain decisions. Part of ownership will be described in relation to the stack and the heap later in this chapter, so here's a brief explanation in preparation. Both the stack and the heap are part of memory available to the code to use at runtime, but they are structured in different ways. The stack stores value in order it gets them and removes the value in the opposite order. like when you stack things, which that makes sense. First in, last out. Yeah, first in, last out. This refers to as last in, last in, first out. Sorry, last in, first out. Think of a stack of plates. When you add more plates, you put them on top of the pile, and when you need a plate, you take it off the top. Adding or removing plates from the middle or bottom won't work as well. Adding data is called pushing onto the stack, and removing data is called popping off of the stack. All data stored on the stack must have a known fixed size. Data with an unknown size at compile time or a size that might change must be stored on the heap instead. The heap is less organized. When you put data on the heap, you request a certain amount of space. The memory allocator finds an empty slot in the heap that's big enough, marks it as being used, and returns a pointer, which is the address of the location. This process is called allocating on the heap and is sometimes abbreviated just allocating. Pushing values onto the stack is not considered allocating. Because the pointer on the heap is known, fixed size, you can store the pointer on the stack, but when you want the actual data, you must follow the pointer. That makes sense. Think of being seated at a restaurant. When you enter, you state the number of people in your group, and the staff finds an empty table that fits everyone and leads you there. If someone in your group comes late, you can ask where you've been seated. If someone in your group comes late, they can ask where you've been seated to find you. Yep. Pushing to the stack is faster than allocating on the heap because the allocator never has to search for a place to store new data. That allocation is always at the top of the stack. Comparatively, allocating space on the heap requires more work because the allocator must find a big enough space to hold the data, then perform bookkeeping to prepare for the next allocation. Accessing data on the heap is slower than accessing data on the stack because you have to follow the pointer to get there. Contemporary processors are faster if they jump around less in memory. Continuing the analogy, consider a server at a restaurant taking orders from many tables. It's most efficient to get all the orders at one table before moving on to the next table. Taking an order from table A, then taking an order from table B, then one from A again, and then one from B again would be a much slower process. By the same token, a processor can do this job better if it works on data that's close to the other data as it is on the stack rather than farther away as it can be on the heap. Allocating a large amount of space on the heap can also take time. Yes, okay. When your code calls a function, the value passes into the function, including potentially pointers to data on the heap. And the function's local variables get pushed onto the stack. When the function is over, those values get popped off the stack. Keeping track of what parts of the code are using what data on the heap, minimizing the amount of duplicate data on the heap, and cleaning up unused data on the heap so you don't run out of space are all problems that ownership addresses. Once you understand ownership, you won't need to think about the stack and heap very often, but knowing that the main purpose of ownership is to manage heap data can help explain why it works the way it does. Ownership rules. First, let's take a look at the ownership rules. Keep these rules in mind as we work through the examples that illustrate them. Each value in Rust has a value that's called its owner. There can only be one owner at a time. When the owner goes out of scope, the value will be dropped. That's good to know. I mean, that happens in JavaScript too. Well, I mean, there's no owner, but when a value is out of scope, you can't access the value anymore. Maybe the value still stays there in memory somewhere, which I guess that kind of makes sense too. but you can't access it anymore. Variable scope. Now that we're past basic Rust syntax, we won't include all the function main code in examples. So if you're following along, make sure you put the following examples inside the main function manually. As a result, our examples will be a bit more concise, letting us focus on the actual details rather than boilerplate code. As a first example of ownership, we'll look at the scope of some variables. The scope is a range within a program for which an item is valid. Take the following variable, s equals hello. S is not valid here. It's not yet declared. S is valid from this point forward. Do stuff with S. This scope is now over and S is no longer valid. In other words, there are two important points at this time. When S comes into scope, it is valid. It remains valid until it goes out of scope. At this point, the relationship between scope and when variables are valid is similar to that in other programming languages. Now we'll build on top of this understanding by introducing the string type. To illustrate the rules of ownership, we need a data type that's more complex than those we covered in data type section of chapter 3. The types covered previously are all known size, can be stored on the stack and pop off the stack when their scope is over, and can be quickly and trivially copied to make new independent instances of another part of code if another part code needs to use the same value in a different scope. But we want to look at data that is stored on the heap and explore how Rust knows when to clean up the data, and the string type is a great example. We'll concentrate on the parts of the string that relate to ownership. These aspects also apply to other complex data types, whether they are provided by the standard library or created by you. We'll discuss string in more depth in chapter 8. We've already seen string literals, where a string value is hard-coded into a program. String literals are convenient, but they aren't suitable for every situation in which we may want to use text. One reason is that they're immutable. Another is that not every string value can be known when we write our code. For example, what if we want to take user input and store it? For these situations, Rust has a second type, string. Okay. This type manages data allocated to the heap, and as such is able to store an amount of text that is unknown to us at compile time. You can create a string from a string literal using the from function, like so. Okay. You can create a string from a string literal using so string literals are convenient. Okay, so I guess this is a string literal. Maybe. No. This is a string literal. So it's like you can do like let sentence equals hello world. That's a string literal, and then you let s equals string from sentence, and that is a string that's just a string. That's just a string, and that string can be dynamically changed. So you could do like let s equals string s plus dynamically changing string. Yeah. And then you can, like, you know, print line why is this so hard? Yeah. Oh, you can't print line S. Oh, okay. Yep. So you have to do like this, like this. But you can't do you can't do like sentence plus can't do this, because sentence is a string and you can't concatenate two strings because you have to know the size of a string so this is like and str, and this is actually a string. Yeah. And can't do this. But you can do this. Line, quote, and then comma s plus this can grow like crazy. Yeah. Okay. Yep. The double colon operator allows us to use the namespace, to namespace this particular from function from the string type rather than using some sort of name like string from. We'll discuss the syntax more in the method syntax section in chapter 5 when we talk about namespacing and modules in chapter 7. I don't like this from. Feels weird to me. String from. Like, why is this called from? I can't really think of a reason to call this from. But maybe I can look that up later. This kind of string can be mutated. Let mut s equals string from hello s dot push str comma world. Okay, so this string type has a push string. Yeah, so it's like a array of strings, or it's like a vector of characters. So yeah, maybe this concatenation is not the way to do it. Really what I should be doing is dot push str, and then like that. That's what it really wants me to do. And then this I can dot push str. Yeah. Oh, that won't let me method. Oh, it doesn't like that. But I can just do s, right? Oh. It won't let me do that. That's weird. Can I do dot parse dot expect Not a string. No. Oh. Why am I getting that there? I don't know. Let's keep reading. Oh, wait. I should be able to do that. Oh. Wait. Should I have made this MUT? Oh, wait. So I was shadowing S, but I can just make that mutable and then just do that, right? Okay, so that's what they do here. Okay. I forgot about the mutable thing. I was using a shadow. I was shadowing S. And then this was maybe returning nothing for some reason. I don't know what I was doing wrong there. But anyways. So what's the difference here? Why can string be mutable but literals can't? The difference is how the two types deal with memory and allocation. In the case of string literal, we know the contents at compile time, so the text is hard-coded directly into the final executable. This is why string literals are fast and efficient, but these properties only come from the string literal's immutability. Unfortunately, we can't put a blob of memory into the binary for each piece of text whose size is unknown at compile time and whose size might change while running the program. With the string type, in order to support a mutable growable piece of text, we need to allocate an amount of memory on the heap unknown at compile time to hold the contents. This means the memory must be requested from the memory allocator at runtime. We need a way of returning this memory to the allocator when we're done with our string. The first part is done when we call string from. Its implementation requests the memory it needs. This is pretty much universal in programming languages. However, the second part is different. In languages with a garbage collector, the garbage collector keeps track of and cleans up memory that isn't being used anymore, and we don't need to think about it. In most languages without a garbage collector, it's our responsibility to identify when memory is no longer being used and call code to explicitly return it, just as we did to request it. Doing this correctly has historically been a difficult programming problem. If we forget, we'll waste memory. If we do it too early, we'll have an invalid variable. If we do it twice, there's a bug too. We need to pair exactly one allocate with exactly one free. Rust takes a different path. The memory is automatically returned once the variable that owns it goes out of scope. Here's a version of our scope example in list 4.1 using string instead of string literal. So here S is valid from this point forward. You do stuff with S, and then this scope is over and S is no longer valid. Okay, that's pretty much the same. There's a natural point at which we can return the memory our string needs to the allocator when S goes out of scope. So here, when the variable goes out of scope, Rust calls a special function for us. The function is called drop, and it's where the author of string can put the code to return the memory. Rust calls drop automatically at the closing curly break. In C++, this pattern of deallocating resources at the end of an item's lifetime is sometimes called resource acquisition, is initialization, or RAII. The drop function in Rust will be familiar to you if you've used RAII patterns. This pattern has a profound impact on the way Rust code is written. It may seem simple right now, but the behavior of code can be unexpected in more complicated situations when we want to have multiple variables use the data we've allocated to the heap. Let's explore some of those situations now. Ways variables and data interact, move. multiple variables can interact with the same data in different ways in Rust. Let's look at an example using an integer in listing for 2. So let x equals 5, let y equal x. So y equals 5. We can probably guess what we're doing here. Bind the value x of 5 to x, then copy the value in x and bind it to y. So now we have two variables, x and y, both equal 5. This is indeed what is happening because integers are simple values with a known fixed size, and these two 5 values are pushed onto the stack. Now let's look at the string version. Here's the string, s1 hello, s2 equals s1. This looks familiar, so we might assume that the way it works would be the same. That is, the second line would make a copy of the value in s1 and bind it to s2, but isn't quite what's happening. In figure 4.1, we see what's happening to strings under the covers. A string is made up of 3 parts, shown on the left: a pointer to memory that holds the content of the string, a length, and a capacity. The group of data is stored on the stack. On the right is the memory on the heap that holds the contents. So this is a pointer that points to this index. There's also a length, so you know that starting from here you count to 5. 1, 2, 3, 4, 5. And this says that the maximum number of characters is 5, which is probably bad if you're using this as a string, because you probably want to change it eventually. But anyways, the length is how much memory in bytes the content of string is currently using. The capacity is the total amount of memory in bytes that the string has received from the allocator. The difference between length and capacity matters, but not in this context, so for now it's fine to ignore the capacity. When we assign S1 to S2, okay, so they point to the same thing. The string data is copied, meaning we copy the pointer, the length, and the capacity that are on the stack. We do not copy the data on the heap that the pointer refers to. In other words, the data representation in memory looks like figure 4.2. The representation does not look like figure 4.3, which is what memory would look like if Rust instead copied the heap data as well. If Rust did this, the operation S2 equals S1 could be very expensive in terms of runtime performance if the data on the heap were large. Yeah. So earlier we said that when a variable goes out of scope, Rust automatically calls the drop function and cleans up the heap memory for the variable, but in 4.2 shows both data pointers pointing to the same location. This is a problem when S2 and S1 go out of scope. They will both try to free the same memory. This is known as a double free error and is one of the memory safety bugs we mentioned previously. Freeing memory twice can lead to memory corruption, which can potentially lead to a security vulnerability. To ensure memory safety, after the line let S2 equal S1, consider S1 Rust considered S1 as no longer valid. Therefore, Rust doesn't need to free anything when S1 goes out of scope. Check out what happens when you try to use S1 after S2 is created. It won't work. Instead, you'll get an error that prevents you from using the invalidated reference. Value borrowed here has after move. Moved occurred because S1 has type string, which does not implement the copy trait. Value moved here, value borrowed after move. So that's what it means by ownership, because S1 no longer owns the string, S2 owns it. So if you've heard the term shallow copy and deep copy while working with other languages, the concept of copying the pointer length capacity without copying the data probably sounds like making a shallow copy. But because Rust also invalidates the first variable, instead of calling it a shallow copy, we call it it's known as a move. In this example, we would say that S1 was moved to S2. So what actually happens is shown in figure 4.4. So that solves our problem. With only S2 valid, when it goes out of scope, it alone will free the memory and we're done. In addition, there's a design choice that's implied here. Rust will never automatically create deep copies of your data. Therefore, any automatic copying can be assumed to be inexpensive in terms of runtime performance. Okay. That's interesting. Kind of automatic copying. So you can like explicitly copy something though and say that like make another S2 and then literally put the words hello in there or whatever. If we do want to deeply copy the heap data of the string, not just the stack data, we can use the method called clone. We'll discuss the syntax in chapter 5, but because methods are a common feature in many programming languages, you've probably seen them before. Yeah, so you can clone it if you really want. This works just fine and explicitly produces the behavior shown in figure 4.3, where the heap data does get copied. When you see a call to clone, you know that some arbitrary code has been executed, and that code may be expensive. It's a visual indicator that something different is going on. Stack only data copy. There's another wrinkle we haven't talked about yet. The code using integers, part of which was shown in 4.2, works and is valid. So that's 5.5. This code seems to contradict what we just learned. We don't have to call clone, but this is on the stack, so that's different, right? But X is still valid and wasn't moved into Y. The reason is that these types, such as integers, have a known size at compile time and are stored entirely on the stack, so copies of the actual values are quick to make. This means there's no reason to we would want to prevent X from being valid after we create the variable Y. In other words, there's no difference between deep and shallow copying here, so calling clone wouldn't do anything different from the usual shallow copying, and we can leave it out. Yeah, because it's on the stack. There's no pointer because we already know where it is. You just have to pop it off the stack. Rust has a special annotation called the copy trait that we can place on types that are stored in the stack like integers are. We'll talk more about traits on chapter 10. If a type implements the copy trait, a variable is still valid after assignment to another variable. Rust won't let us annotate a type with copy if the type or any of its parts has implemented the drop trait. If the type needs something special to happen when the value goes out of scope, we add the copy annotation to the type. We'll get a compile time error. To learn about how to add copy annotation to your type to implement the trait, see derivable traits in Appendix C. So what types implement the copy trait? You can check the documentation for the given type to be sure, but a general rule, any group of simple scalar values can implement copy, and nothing that requires allocation or something from a resource can implement copy. Here are some types that implement copy. Booleans are not scalar types. Tuples and characters. Oh, but I32, for example, I32. Okay, but this, okay, tuples if it only contains types that also implement copy. What about arrays? Because they all contain the same type. I don't know. I don't see why you would use copy, though. I don't really understand why you would use copy. But they'll talk about it in chapter 10. Because if you can just do this, why would you do x.copy? Also, that's just typing 5 extra characters. Right? I don't know why you would do that. Ownership and functions. So the semantics for passing a value from a function are similar to those of assigning a value to a variable. Passing a variable to a function will move or copy, just as assignment does. Listing 4.3 has an example with some annotations showing where variables go into and out of scope. So here's S, here's our hello, and then here's a function called take ownership of S, and then here we have x equals 5, and then here's a make copy of 5. So and then take ownership is some string comes into scope, and then you print the string, and then it goes out of scope, and drop is called. Then there's nothing in that string anymore. But this is kind of like the x equals y thing. So like in here, I guess s equals some string now, and then some string here you can't call s, even though that's s could be like a global string. Like if we had this function in here, you wouldn't be able to call s in here because some string would take ownership of s because they're pointing to the same string. But then once the function is done, you can call s again out here. But then here's the copy thing. X comes into scope. X would be moved into the function, but I32 is copied, so it's okay to still use X afterwards. Oh, S's value is moved into the function, so it's no longer valid here. Oh, so we can't use S here. Okay. So what I was saying what isn't true. So wait, here some string goes out of scope and drop is called. The backing memory is freed. Some string comes into scope. Some integer comes into scope. Here some integer goes out of scope, nothing special happens. I wonder, but can you use S after? I mean, I guess if it's no longer valid from here on out. That's interesting. So it doesn't go back. The ownership doesn't revert back to the original. At this is just gone forever. If we try to use S after the call take ownership, Rust will throw a compiler error. These static checks protect us from mistakes. Try adding code to main that uses S and X to see where you can use them and where the ownership rules prevent you from doing so. Let's give it a try. I mean, yeah. just delete my thing. And so I can't use s here. Print line. Yeah. Yep, borrowed on move. But here, you can use print line. Because x is on the stack. So, there's two x's. There's a some integer and there's an x. Some integers on top of a 5, and then once you're done with make copy, some integer comes off, but 5 is still, x equals 5 is still underneath it. And then once print line is done, x goes out of scope and it pops off the stack. Then, but because s's values removed, nothing special happens here. Yeah, and so since this took ownership, you'll never get s back. That seems kind of crazy. That seems really inconvenient. But I guess you just have to be like cognizant of that. Okay. Yeah. So returning values can also transfer ownership. Listing 4 shows an example of a function that returns some value with a similar annotation listed in 4.3. I think I get it. I think I'm going to skip this. Ownership of a variable follows the same pattern every time. Assigning a value to another variable moves it. When the variable that includes data on the heap goes out of scope, the value will be cleaned up by drop unless ownership of the data has been moved to another variable. Oh. Well, I mean, but if it takes ownership in a function, once the function's out of scope, how I just don't see how you could save the value. But I don't know. Well, this works. Taking ownership and then returning ownership with every function is a bit tedious. What if we want to let a function use a value but not take ownership? It's quite annoying that anything we pass in also needs to be passed back if we want to use it again, in addition to any data results from the body of the function that we might want to return as well. Rust does let us use return multiple values using tuples as shown in list 4.5. So okay, so you can return a string in a U size. But there's too much ceremony, but this is too much ceremony and a lot of work for a concept that should be common. Luckily for us, Rust has a feature for using a value without transferring ownership called references. Okay. References and borrowing. So the issue with the tuple code in 4.5 is that we return the string to the call function. So we can still use the string after the call to calculate length because the string was moved to calculate length. Instead, we can provide a reference to the string value. A reference is like a pointer in that it's an address we can follow to access data stored at the address that's owned by some other variable. Unlike a pointer, a reference is guaranteed to point to a valid value of a particular type. Here's how you would define and use a calculate length function that has a reference to an object as a parameter instead of taking ownership of the value. So use the and. Okay, so here I can pass it and s. Oh, I can't. I found a pointer. Oh, okay. So here you have to expect a pointer to a string. A pointer to a string. Yes, instead. And now I can call this outside. Yes. Yeah. Okay. First, notice that this is a tuple code in the variable declaration. So, where's the tuple? First, notice all the tuple code in the variable declaration. And the function return value is gone. What? Oh. I don't know what it's talking about. The tuple code? Where's 4.5? That's 4.3. That's 4.4. This is 4.5. Okay. That's 4.5. So the tuples, the tuple is gone. Okay. Yeah. And then what else did it? And the function return value is gone. Yes. No return value. That's the return value, and it's not there. And so, yeah. Second, note that we pass and s1 into calculate length, and in its definition we take and string rather than string. These ampersand represent references, and they allow you to refer to some value without taking ownership of it. So s has a pointer to a pointer that points to the index. So note the opposite of referencing by using and is dereferencing, which is accomplished with the dereference operator star. We'll see some use of dereference operator in chapter 8 and discuss details of dereferencing in chapter 15. Hold on a second. My cat. What's up? Okay. There's a cat stream now. Let's see. Okay, so let's take a closer look at the function call here. Let s1 equal string from hello. Let len equal calculate length and s1. Okay, so and s1 syntax lets us create a reference that refers to the value of s1 but does not own it. Because it does not own it, the value it points to will not be dropped when the reference stops being used. Likewise, the signature of the function uses and to indicate that the type of parameter s is a reference. Let's add some explanatory annotation. So here s is a reference to a string. Here s goes out of scope, but because it does not have ownership of what it refers to, nothing happens. So the scope in which the variable s is valid is the same as any function parameter scope, but the value pointed to by the reference is not dropped when s stops being used because s doesn't have ownership. When functions that reference as parameters instead of actual values, we won't need to return the value in order to give back ownership because we never had ownership, and call the action of creating a reference borrowing. As in real life, if a person owns something, you can borrow it from them. When you're done, you can give it back. You don't own it. So what happens if you try to modify something we're borrowing? Try the code. Spoiler alert, it doesn't work. Okay. So the error is, help, consider changing this to a mutable reference. Oh, you can make a mutable reference. Some string is a AND reference, so the data it refers to cannot be borrowed as mutable. As variables are immutable by default, so are references. We're not allowed to modify something if we have a reference to it. Mutable references. We can fix the code from listing 4.6 by allowing us to modify a borrowed value that was with just a few small tweaks. Instead, use a mutable reference, so and muts. So first we change s to be mutable, then we create a mutable reference with an muts, where we can call the change function and update the function signature to accept a mutable reference with some string and mute string. This makes it very clear that the change function will mutate the value it borrows. Mutable references have one big restriction. You can only have one mutable reference to a particular piece of data at a time. This code that attempts to create two mutable references to S will fail. First mutable borrower occurs here, second mutable borrower occurs here. This error says that the code is invalid because we can borrow S as a mutable more than once. We cannot borrow S as mutable more than once at a time. The first mutable borrow is in R1 and must last until it's used in the print line. But between the creation of the mutable reference and its usage, we try to create another mutable reference in R2 that borrows the same data as R1. The restriction preventing multiple mutable references to the same data at the same time allows for mutation, but in a very controlled fashion. It's something that new rustaceans struggle with because most languages let you mutate whenever you like. The benefit of having this restriction is that Rust can prevent data races at compile time. A data race is similar to a race condition that happens when these behaviors occur. Two or more pointers access the same data at the same time. At least one of the pointers is being used to write to the data. There's no mechanism being used to synchronize access to the data. Okay. Data races cause undefined behavior and can be difficult to diagnose and fix when you're trying to track them down. At runtime, Rust prevents this problem by refusing to compile code with data races. As always, we can use curly braces to create a new scope, allowing for new multiple mutable references, just not simultaneous ones. Okay, Rust enforces a similar rule for combining mutable and immutable references. This code results in an error. No problem, no problem. And then, since it's mutable, that's a problem. Okay. We almost cannot have a mutable reference while we have an immutable one at the same one to the same value. Users of an immutable reference don't expect the value to suddenly change out from under them. However, multiple immutable references are allowed because no one who is just reading the data has the ability to affect anyone else's reading of the data. Note that the reference's scope starts from where it is introduced and continues through the last time the reference is used. For instance, this code will compile compile because the last usage of the immutable reference, the print line, occurs before the mutable reference is introduced. Okay. Yep. So the scope of the immutable reference R1, R2, and after the print line where they are last used, which is before the mutable reference 3 is created, these scopes don't overlap, so this code is allowed. The ability to compile of the compiler to tell that a reference is no longer being used at a point before and the end of the scope is called non-lexical lifetimes, NLL for short. You can read more about them in the edition guide. Okay, which I think I have multiple of those. But anyways, even though borrowing errors may be frustrating at times, remember that it's the Rust compiler pointing out a potential bug early at compile time rather than at runtime and showing you exactly when the problem is. Then you don't have to track it down yourself, track down why the data isn't what you thought it was. Dangling references. In languages with pointers, it's easy to erroneously create a dangling pointer, a pointer that references a location in memory that may have been given to someone else by freeing some memory while preserving a pointer to the memory. But in Rust, by contrast, the compiler guarantees that references will never be dangling references. If you have a reference to some data, the compiler will ensure that the data will not go out of scope before the reference to the data does. Let's try create a dangling reference to see how Rust prevents them with the compiler time. So here we let reference to nothing equal dangle function, and then dangle is a pointer, expects a pointer to a string, or returns a pointer to a string. Let s equal string from hello, and then you return the pointer to s. But this s goes out of scope, so this would point to nothing. And so expected name lifetime parameter. This function's return type contains a borrowed value, but there's no value for it to be borrowed from. Consider using the static lifetime. And static string. This error message refers to a feature we haven't covered yet, lifetimes. We'll discuss lifetimes in detail in chapter 10, but if you disregard the part about lifetimes, the message does contain the key to why the code is a problem. This function returns type contains a borrowed value, but there's no value to be borrowed from. Let's take a closer look at exactly what's happening at each stage of the dangle code. So dangle returns a reference to a string. S is a new string. We return the reference to string s. Here s goes out of scope and is dropped. Its memory goes away. Because s is created inside dangle, when the code of dangle is finished, s will be deallocated. But we try to return a reference to it. That means this reference would be pointing to an invalid string. That's not good. Rust won't let us do this. Solution here is to return string directly. This works without problem. Ownership is moved out and nothing is deallocated. I don't even know why you would try to do this. But I guess it happens by accident all the time, and that's why this has to be a feature. Okay. So slice type. This is the last bit, and then I think I'm going to head out. So let's see. A slice type. Slices let you reference a contiguous sequence of elements in a collection rather than the whole collection. A slice is a kind of reference, so it does not have ownership. Here's a small programming problem, not program. Write a function that takes a string that returns the first word it finds in that string. If the function doesn't find a space in the string, the whole string must be one word, so the entire string would be returned. Let's work through how we'd write a signature of this function without using slices to understand the problem that slices will solve. Okay, sorry, what's the problem? Write a function that takes a string, okay, returns the first word it finds in that string, okay. If the function doesn't find a space in the string, the whole string must be one word, so the entire string should be returned. Yeah, that makes sense. Let's work through how we'd write the signature of this function without using slices to understand the problem that slices would solve. So this is a function, and you're going to return a pointer to a string, or you're going to take a pointer to a string. So the first word function has a reference to a string as a parameter. We don't want ownership, so this is fine, but what would we return? We don't really have a way to talk about part of a string. However, we could return the index of the end of the word indicated by a space. Let's try that as shown in listings 4.7. So end string, so we return usize. Let bytes equals s dot as bytes for I point item reference to item in bytes dot iter that enumerate. If item equals byte, return I, and then s dot lens. That's pretty confusing, but yeah. So let's try that. However, we could return the index of the end of the word. Yeah. Okay. Because we need to go through the string element by element and check whether a value is a space, we'll convert our string to an array of bytes and use byte as method. Okay, so this is, yeah, and then for each byte, if the byte is B, then you return that, you return that index, and that's the index that the word ends, because it's a space, because there's no byte there, because it's a blank line. Yeah, okay. Next, we create an iterator over the array of bytes using iter method. And we discuss iterators in more detail in chapter 13. For now, know that iter is just a method that returns each element in a collection, and that enumerate wraps the iter and returns each element as part of a tuple instead. Okay. The first element of the tuple returned from enumerate is the index. The second element is a reference to the element. This is a bit more convenient than calculating the index ourselves. Because the enumerate method returns a tuple, we can use patterns to destruct that tuple. We'll be discussing patterns in chapter 6. In the for loop, we specify a pattern that has I for the index in the tuple and an item reference to the item for a single byte in the tuple. Because we get a reference to the element from .iter.enumerate, we used an in the pattern. Okay. Inside the for loop, we search for the byte that represents the space by using a byte literal syntax. If we find space, we return the position. Otherwise, we return the length of the string by using s.lens. Okay, yeah. because this might not return anything. If it doesn't match this, it just skips the if, and then the for loop is complete, and then but if it returns I, then the function ends. Okay. Yeah. We now have a way to find the index of the end of the first word in the string, but there's a problem. We're returning a U size on its own, but it's only a meaningful number if the context of the and string. In other words, because it's a separate value from string, there's no guarantee that it will still be valid in the future. Consider the program in list 4.8 that uses the first word function. So mute s equals string hello world, and then let word equal first a reference to s, first word. So this is actually an int or a u32, and it equals 1, 2, 3, 4, 5, 5, 6. It's 6, or 0, 1, 2, 3, 4, 5. So it's 5. Yeah, word will get the value 5. This empty string makes it blank. Word still has the value 5. That there's no string. We can meaningfully use the value 5. The word is now totally invalid. Yeah. This program compiles without any error, and would also do so if we use word after calling it as clear, because word isn't connected to the state of s at all. Word is still contains the value 5. We could use value 5 as a variable s to try to extract the first word out, but this would be a bug because the contents of s would change since we have, say, 5 in word. Having to worry about the index in word getting out of sync with the data in s is tedious and error prone. Managing these indexes is even more brittle if we write a second word function. Its signature would have to look like usize. Right. Because it would have to start, it would have to be the first index would be the first usize, and then the second index would be the end of the string. Or if the string has 3 words, it would be, yeah, whatever the last number is. Now we're tracking a starting and ending index, and we have to have even more values that were calculated from data in a particular state but aren't tied to that state at all. We have 3 unrelated variables floating around that need to be kept in sync. Luckily, Rust has a solution to this problem: string slices. A string slice is a reference to a part of a string. So it looks like this. Let hello equal reference s 0, 5, and then hello reference as 6 to 11. Rather than reference the whole string, hello is a reference to the portion of the string specifically specified in the extra 0.5 bit. We create slices using a range. So this is like the other range. It's inclusive for the first value and not inclusive of the second value. 1, 0, 1, 2, 3, 4, 5. Yep. We create slices using range within brackets by specifying, and I guess you can do equal 5 or equal 4. Yeah, if you wanted to. Either way, I think, without the equal looks better anyways. So starting index, ending index, where the starting index is the first position of the slice and the ending index is one more than the last position of the slice. Internally, the slice data structure stores the starting position and the length of the slice, which corresponds to the ending index minus starting index. So in the case let world equal, world would be a slice that contains a pointer to the byte at the index of 6 of S with the length value of 5. Okay, so yeah, there's the pointer. So word is a pointer to part of the string. With Rust ... range syntax, if you want to start at index 0, you can drop the value before 2 periods. In other words, they are equal ... 2. By the same token, if your slice includes the last byte of the string, you drop trailing numbers, and those are equal. Okay. You can also drop both values to take a slice of the entire string, so those are equal. Okay, so that's just the whole word, huh? Now, string slice range indexes must occur at valid UTF-8 character boundaries. If you attempt to create a string slice in the middle of a multiple byte character, your program will exit in an error. For the purpose of introducing string slices, we're assuming ASCII only in this section. More thorough discussion of UTF-8 handling is in storing UTF-8 encoded text with strings in Chapter 8. With all this information in mind, let's rewrite first word to return a slice. The type that signifies string slice is written as and str. So that's what a string literal type is, isn't it? So here we return str, okay, and then here, okay, so we still have to get a list of bytes, but then, and we still have to iter and enumerate those. But if item equals I, then we return the pointer, or we return the whole string. So we get the index for the end of the word in the same way we did in listing 4.7 by looking at the first occurrence of a space. When we find a space, we return a starting slice using the start of the string and the index of the space at the starting and ending indexes. Now, when we call first word, we get back a single value that is tied to the underlying data. The value is made up of a reference to the starting point of the slice and the number of elements in the slice. Returning a slice would also work for second word function. Right. Now we have a straightforward API that's much harder to mess up because the compiler will ensure the reference into the string remains valid. Remember the bug in the program in listing 4.8 when we tried to get the index to the end of the first word but cleared the string and our index was invalid. The code was logically incorrect but didn't show any immediate errors. Our problem would show up later if we kept trying to use a first word index with an empty string. Slices make this bug impossible. Let us know we have a problem with our code much sooner. Using the slice version of first word will throw a compile time error. So if we cleared it, there's an error. Immutable borrow occurs here. Mutable borrow occurs here. Immutable borrow later used here. Recall from the borrowing rules that if we had an immutable reference to something, we cannot also take a mutable reference, because clear needs to truncate the string. It needs to get a mutable reference. The print line after the call to clear uses the reference in Word, so the immutable reference must still be active at that point. Rust disallows the mutable reference in clear and the immutable reference in Word from existing at the same time. The compilation fails. Not only has Rust made our APIs easier to use, but it's also eliminated an entire class of errors at compile time. String literals are slices. Recall that we talked about string literals being stored inside the binary. Now that we know about slices, we can properly understand string literals. So this is a literal. The type of S here is an S. It's a slice pointing to a specific pointer in the binary. This is also why string literals are immutable, and S as is an immutable reference. Yeah, it's a slice pointing to that. Interesting. So string slices as parameters. Knowing that you can take a slice of a literal and string values leads us to one more improvement on first word, and that's its signature. So this, a more experienced Rustacean would write the signature as below, because it allows us to use the same function on both n string value and s string value. It would allow us to use the same function on both. Really? So it returns a string and you put in a string, or you put in a slice and you return a slice. If we have a string slice, we can pass that directly. If we have a string, we can pass a slice of the string or a reference to the string. This flexibility takes advantage of dereference coercion, a feature we will cover in implicit dereference coercion with functions and methods in chapter 15. Defining a function to take a string slice instead of a reference to a string makes our API more general and useful without losing any functionality. I see. Because this is both a reference to a string and a slice, but this is only a reference to a string. So my string is a string from hello world. So this is dynamic, the first word. So this is a reference to a slice. And then let first word be a reference to the whole. This is the whole word. First word also works on references to strings, which are equivalent to the whole slice of the string. Yeah. You can do a slice to the whole string, and you can do a slice to part of the string. Okay. Other slices. String slices, as you might imagine, are specific to strings, but there's more general slice types too. Consider this array. Just as we might want to refer to part of a string, we might want to refer to part of an array. We'd like to do this like that, you know, where, so here's an array, here's a slice of an array. So we do like, we point to A, and we do 2, 3, 4, and then we I don't know what this assert equals. Slice, comma, and 2, 3. Oh, I guess this wants to assert what values are in here. So it'd be 3, 4, I guess. Or 2, 3 would be these spots. So it would be 0, 1 in this slice, right? Oh, well, I guess since it's referencing this, it'd be 1, 2. So this slice has a type of and a reference to an array of I32 or U32s even, unsigned. It works the same way a string slices do. Oh, I think this is U32 because that's the default, isn't it? It works the same way that string slices do by storing a reference to the first element and a length. You'll use the kind of slice for all sorts of collections. We'll discuss these collections in detail when we talk about vectors in Chapter 8. Summary: the concept of ownership, borrowing, and slices ensure memory safety in Rust at compile time. Rust language gives you control over your memory usage in the same way as other programming languages, but having the ownership of data automatically clears up that data when the owner goes out of scope means you don't have to write and debug extra code to get this control. Ownership affects how lots of other parts of Rust work, so we'll talk about these concepts further throughout the rest of the book. Let's move on to Chapter 5 and look at the grouping pieces of data together in a struct. Awesome. All right, finally got through that. Well, I said I was going to leave, so I'll see you guys.